Hello everyone, I'm Sui from Rutgers. I'm glad to introduce our paper titled Sensor Placement for Globally Optimal Coverage of 3D Embedded Surfaces. This is a joint work with my colleague Kai Gao, Professor Gong, and my advisor, Professor Jingjin. We start with the scenario of hospital sanitization. For this case of disinfecting an ICU, which we need to keep it from certain bacteria or virus. Besides having a mobile robot or human being moving around to do the cleaning task, an effective and fast way to do such task is to deploy static sanitization lights, for example UV lights, inside the room for quick and continuous disinfection. Given a fixed number of these lights, we want to find the optimal placement of these lights so that they can achieve better coverage of the surface of the ICU. This problem also arises in a series of possible application scenarios, as bus or subway disinfection, or in the case of security camera deployment, where we want to find the optimal placement of the surveillance camera so that we can get a more complete view of the room using 360 degrees camera. This work is also related to plenty of previous work, including location optimization, in which people study classical problems as K-center, K-means, and art gallery problems. Our continuing work on optimal set guarding and perimeter guarding also provides an aspect for solving these problems. This work is also related to the area of mobile sensing network and coverage control, where people often use iterative methods to obtain a near optimal solution, and the coverage claiming problem for optimal paths for one or several robots to achieve coverage purpose. Now we provide an outline of the problem studied. Given a bounded workspace S with surface S, sensor plane SC where sensors are placed on, and a team of K robots or sensors, define the coverage quality of a point O on S as f C1 to CK O, with C1 to CK as the sensor locations. The natural question comes into place that what are the locations to place these robots, which in this setup are static locations? Based on different quality definition and different objectives, we studied three different models. They are bare visibility-based model, which maximizes the area of the surface seen by the robot, the quality maximization model, which maximizes the minimum coverage quality of a point on the surface, and the cumulative quality model, which maximizes the area of the surface which can have enough coverage quality. We want to mention here that all these problems are computationally intractable due to their reductions from related 2D visibility or coverage problems. The first and the most simplistic model is the visibility model, when visibility is the only thing being considered. The sensing quality for point O is 1, if it is visible to at least one sensor. The function vis-CIO here indicates whether the surface point O is visible to center location point CI. This objective is to maximize the area of the surface visible to the sensors, that is, the support of the function f. Now we provide two general preprocessing steps, which are also used for the other two models. In the first step, we discretize the surface with a set of points, denoted as O1 and O together to On. So the problem of maximizing the area covered is transformed into maximizing the number of sampled surface points covered. Then we discretize the sensor location choices to Ci to Cm and precompute the pairwise visibility between each sampled surface points and sampled candidate sensor location points. So now the problem can be easily transformed into an integer programming model, where we have n plus m variables, where yi indicates whether surface point oi is covered, which are binary variables, and the binary variable zi indicates whether candidate center location ci is selected. The first constraint builds the criteria for a point being covered, and the second constraint limits the number of sensors. Naturally, the objective is set to maximize the number of sampled points covered. By solving this model, we can get an optimal solution of placing 3 sensors on top of an SU to get a best coverage like this. In the quality maximization model, the sensing quality of a point O is determined by the sensor closest to it while still visible to it. In this case, we minimize the maximum distance from a point on the surface to its nearest sensor location. When assuming full visibility, this problem is quite similar to the formulation of the Euclidean case-center problem. However, in the problem of placing sensing robots, the robot's location cannot be anywhere in the environment due to considerations of human movement and physical constraints. So we can find the robot location to the roof of the environment. This is a significant difference from the theoretical Euclidean case-center problem. In the case of assuming full visibility, we can still get a two approximation algorithm by applying farthest point clustering combined with spatial projection. While in the case of full visibility cannot be guaranteed. For example, some surface points beneath the bed or seat cannot be seen by a camera or light. We can only guarantee a percentage of the surface being covered. Still, we can apply integer programming as a basic tool to test whether a certain coverage radius R can satisfy those constraints. In the ILP model, we substituted the previous objective on the number of sampled points covered with the constraints on the minimum number of sampled points covered with respect to the coverage ratio required ρ. By testing the feasibility of this model, we can see whether a coverage radius R can satisfy the coverage requirement, and by applying the binary search on the coverage radius R, we can get a minimum coverage radius. For example, by using 4 sensors and a required coverage ratio of 80, we can get a minimum coverage radius that can achieve a coverage quality like this. However, solving the integer programming model turns out to be quite time-consuming when there are more constraints brought in the ILP model or there are real values in the ILP model. To this end, we proposed an cost model plus local improvement algorithm-based methodology to solve this problem. For example, if a cost model can obtain 2 approximate results, but it can be further improved by 25%, then we still create a 1.5 globally optimal solution. In our experiment, we see that this methodology creates up to 20 times faster algorithm, but still have similar coverage results. The last and more complicated cumulative quality model considers both distance from a sensor location to the surface points and the norms on the surface. The right picture shows the correlation between a surface point with norm pointing up and the sensing quality provided by sensors at different locations. The objective is to maximize the area of the surface that can have enough coverage quality phi, that is, to maximize the support of the function f minus phi. Similar integer programming-based methods plus local improvement still can be applied. In this model, we can observe that there are real-valued functions, that is, the quality of sensing phi, ci, oi, which have floating values brought into the ILP model, which makes the ILP model quite slow in our experiments. So the importance of a cost model combined with local improvement appears to be more significant. By applying these methods on the surface of a bus, We can obtain coverage results like this using 3 to 5 sensors. Lastly, we present the computational results using 3 realistic scenarios: ICU room, interior of a bus, and the interior of a subway. For the parameter choice, we sampled 20,000 points on the surface and used 1,000 of them for the cost model. 600 candidate sensor locations were sampled with 60 used for the cost model. From the figures of running time, we can observe that most of the scenarios can be solved quite effectively with no more than half an hour for using up to 8 sensors. In the corresponding resulting coverage, it shows that our methods can normally scale up to the point when the coverage quality, that is, the percentage of the surface being covered, or the coverage radius, have reached a plateau. The bar chart on the right picture shows the optimality gap using our method. Except for the larger subway model, the other two models can get a very small optimality gap within a very small time. So, in these experiments, we showed that our methods have high quality and normally low optimality gap in the three models, and demonstrated the effectiveness of the cost model plus local improvement approach in these cases. When we also observed that it normally will cost more time when the coverage quality is about to reach the plateau. Lastly, we present a summary of contributions of this work. Firstly, we formulated a general set of problems as sensor placement for optimal coverage problems, and provided effective integer linear programming-based solver to solve these problems, as well as two approximate results for quality maximization model with full visibility. We also provided a cost model plus local improvement methodology, which is highly efficient and still have similar coverage performance with a pure ILP solver. We did evaluations on 3 realistic instances, the interiors of subway, bus, and ICU, to demonstrate the effectiveness of our methods. So that's all for my talk. Thank you for your time.